Hello and welcome to this episode of Optical Cavity Quantum Electrodynamics. I have labeled it Part 1 because today we will be dealing with the basics. Now, most of you are going to make a first remark that the maths is missing. Yes, the maths is missing. This video has not been made for mathematical accuracy. I have deliberately left out the maths because that is going to make the subject extremely heavy. I have tried to explain the basic concepts in the simplest language possible, and to the best of my ability, I think I have been able to make it accessible even for a layperson. First off, cavity quantum electrodynamics. Cavity QED is a field of study which accesses an important regime involving coupling of single atoms to only a few optical modes. Experimentally, this is made possible by placing single atoms within optical cavities of very high Q. This is so because only one or two electromagnetic modes exist within the cavity, and each of these has a very high electric field strength. The dipole coupling between the atom and the field is very high. This particular slide shows a visual of Kimball and the Mabuchi groups at Caltech. So optical cavity QED is currently a very rich field of research and study. Because of high Q, photons within the cavity have an opportunity to interact many times with the atoms before escaping. Theoretically, this technique presents a unique opportunity to control and study single quantum systems, opening up many opportunities in quantum chaos, quantum feedback control, and quantum computation. No, I've not gone mad, and this is not an interruption. This is my imagination of what quantum chaos would sound like. Now we discuss optical modes. Electromagnetic fields in the presence of metallic boundaries form the practical aspect of an important subject. Generation and transmission of electromagnetic radiation involving metallic structures whose dimensions are close to the involved wavelengths. At much higher infrared frequencies, dielectric optical fibers are extensively used in the telecommunications industry. This is a beautiful image of an optical fiber. Continuing with the discussion on optical modes, a practical solution of great importance is the propagation and excitation of electromagnetic waves in hollow metallic cylinders. If the cylinder has end surfaces, it is called a cavity. Otherwise, a waveguide, usually taking the fields to be sinusoidally time-dependent inside the cavity, we use Maxwell's equations which satisfy the Laplace equation to arrive at the following conclusions/observations. A degenerate or special type of solution having only field components transverse to the direction of propagation are called transverse electromagnetic waves, or TEM modes. This slide shows a schematic of the transverse electric mode and the transverse magnetic mode. The transverse electric mode cannot exist inside a single hollow cylindrical conductor of infinite conductivity. The surface is an equipotential. The electric field therefore vanishes inside. It is necessary to have two or more cylindrical surfaces to support the TEM mode. The familiar coaxial cable and parallel wire transmission line are structures for which this is the dominant mode. An important property of the TEM mode is the absence of the cutoff frequency. The wave number is real for all omega. This is not true for the modes occurring in hollow cylinders. This slide shows the imagery for different cutoff frequencies. Starting from the left, the cutoff frequency being 1 kHz, going up to 1 MHz, and finally to 1 GHz. In hollow cylinders and on transmission lines at high frequencies, there occur two types of field configuration. Their existence can be seen from considering the wave equation satisfied by longitudinal components of the electric and magnetic components and the boundary conditions to be satisfied. Provided the fields are time-varying perfect, conductivity assures that both electric and magnetic fields vanish within the conductor. For the magnetic component, the skin depth is vanishingly small. The presence of surface charges and currents at the interface allows the existence of a normal component of the displacement vector and also a tangential component of the magnetic field. Here I would like to clarify that E represents the electric field, B will always represent the magnetic induction, D represents the displacement vector, and it is H that represents the magnetic field. But the tangential component of E and the normal component of B must always be continuous across the boundary. Thus, for a perfectly conducting cylinder, the boundary conditions give rise to transverse electric and transverse magnetic modes. A cutoff frequency is defined, and for frequencies less than the cutoff frequency, propagation cannot take place. Hence, such modes are called cutoff or evanescent modes. A more technical and scientific representation of the transverse electromagnetic mode, showing the representation of the direction of propagation and how both the electric and magnetic fields run transverse to the direction of propagation. Just cavities do not suffice. We need to understand resonant cavities. An important class of cavities is produced by placing the end faces on a length of a cylindrical waveguide. The end faces are assumed to be plane and perpendicular to the axis of the cylinder. Resonant cavities have discrete frequencies of oscillation with a definite field configuration for each frequency. To excite a particular mode of oscillation, the exciting frequency needs to be chosen exactly equal to the resonant frequency. Here is a visual schematic of what an optical cavity looks like. We next come to high Q. A measure of the sharpness of response of the cavity to external excitation is the Q of the cavity. It is defined as 2 pi times the ratio of the time average energy stored in the cavity to the energy loss per cycle. Hence, Q, which is equal to omega 0, is stored energy upon power loss. Q values of several hundreds or thousands are common for microwave cavities. I'd like to sign off with a visual representation of what a high Q mode looks in comparison to a low Q mode. As I had mentioned in the beginning, this is just the first part of a rather long presentation, and it is going to be continued. I'd like to thank you for watching the video till the end, and I will end by a quote from Edward O. Wilson. Science offers the boldest metaphysics of the age. It is a thoroughly human construct, driven by the faith that if we dream, press to discover, explain, and dream again, thereby plunging repeatedly into new terrain, the world will somehow come clearer, and we will grasp the true strangeness of the universe. And the strangeness will all prove to be connected and make sense. Thank you and bye-bye.